Hey everyone, welcome back. We've got one more technique of integration to work on, and this one is called partial fractions. And what it is, it's actually really just algebra or arithmetic designed to help us deal with integrating functions that are of the form polynomial in the numerator, polynomial in the denominator. So let me just start off with an example. So let's say that we need to integrate 1 over x squared plus x dx. This is definitely not a function for which I know a formula for the integral of. But here's what's true. It turns out that our integrand can be rewritten as 1 over x minus 1 over x plus 1. So it may not be obvious right now, in fact I'm sure it's not obvious, that this function is equal to this function right here, but if you were to get a common denominator over here, you would find out that this piece, or this integrand right here, is exactly equal. And so now, to integrate this, right, we have an easy job. This is natural log absolute value of x. This next piece right here, natural log absolute value of x plus 1 plus c. And by the way, your book will always do this. If possible, it will simplify using rules of logs. This can be rewritten as natural log absolute value x divided by x plus 1 plus c. So what we want to do, what we're going to do in this lecture and in the next lecture, is work on the process of taking a function of this form and rewriting it in simpler pieces. These simpler pieces are called partial fractions, and this method of integration is called partial fractions. So there's the idea, taking integrands of this form, rewriting them in simpler form, the partial fractions, and then once you have it in simpler form, the integral actually becomes easy. So there's the topic for today, partial fractions. So let's say it this way first. So let's say just call this a fact. If p of x and q of x are polynomials with the degree of, I want to say it like this. Yeah, with degree of p of x strictly less than the degree of q of x, then when we look at the fraction p of x divided by q of x, this fraction right here can be expressed as a sum of simpler, let's call them fractions. These are called fractions, and those are called partial fractions. So there's the idea. If we have polynomial over polynomial where the degree of the numerator is strictly smaller than the degree of the denominator, then we can re-express this thing right here, this thing which is called a rational function, polynomial over polynomial, as a sum of simpler fractions. We're going to break this into cases. And the cases all depend on the factorization of the denominator. So case 1, we'll label this distinct linear factors. So let's say if q of x can be factored as a1x plus b1 times a2x plus b2 anx plus bn. So what we have is q of x, our denominator, is factored into a bunch of degree 1 polynomials. So it splits completely into linear factors where none of these match. So let's say where no factors match. Then our rational function p of x divided by q of x is equal to a1, capital A1, divided by little a1x plus b1, plus capital A2, a2x plus b2, plus dot dot dot, plus a sub n, little a n x, plus little b n. So what this is saying is if you can factor the denominator completely into degree 1 pieces, then the rational function can be expressed as constant divided by the first factor, plus some other constant a2 divided by the second factor, plus dot 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 dot, constant divided by the last factor. So let's see this in action. And notice now, I mean, this is not calculus. Once you have factored the rational function, if you were originally asked to integrate the rational function, p of x over q of x, you would instead find these constants, and then you would integrate each of these pieces individual, and each of those would be an easy integral. So let's look at this example here. And I'm not even going to bother integrating right now. I just want to do the process of finding the partial fractions. So 5x plus 3 divided by 2x squared plus 5x plus 3. Now, so let's see, first thing I need to do is factor. So let's see, this will factor as 2x plus 3 and an x plus 1, I think. Right, 2 and 5, right. Okay, so step 1, factor the denominator. And then according to this formula right here, what that tells us is that this can be expressed as a constant over the first factor plus a constant over the second factor. Instead of me using a capital A1 and a capital A2, I'm going to use a capital A and a capital B. So we know that there is some capital A and some capital B, such that this original rational function, polynomial over polynomial, can be expressed in this form right here. So our job now is to figure out which A and B work. So step 1, what I'm going to do is got to get a common denominator. And that's always going to be the first step. When you see this, multiply everything out. So I multiplied the top and the bottom of this first piece by x plus 1, the top and the bottom of this piece by 2x plus 3, and so then the denominator stays 2x plus 3, x plus 1. All right, so there's step 1. Step 2, I'm going to multiply out the numerator. So I get an ax plus a plus 2bx plus 3b, all divided by the same denominator, 2x plus 3, x plus 1. Now, my next step. What I want to do is group the terms. So I see a couple of terms that involve x, and I see a couple of terms that involve a constant. I want to group those together. So what I'll get is a plus 2b times x plus a plus 3b all over 2x plus 3 x plus 1. So let's review those steps real quick. First, express it as constant over the first factor plus constant over the second factor. Get common denominator, multiply out, and then group the terms. At this stage, now we know, looking at this fraction right here, it has to match this fraction right here, which tells us that the numerators have to match. And so notice right here, I've got an a plus 2b times x. that has to equal 5x. So that tells us that a plus 2b has to equal 5. Also, the constant term on the left-hand side is a 3. The constant term on the right-hand side is a plus 3b. So that tells us that a plus 3b has to equal 3. So now what we have is 2 equations and 2 unknowns, and you've learned various ways to solve such equations, or systems of equations. One way is to subtract. And so if I subtract the bottom equation from the top equation, what I get is negative b equals 2, which means b equals minus 2. If b equals minus 2, then we would have, if I substitute that up into the top equation, I get a minus 4 equals 5, so a has to equal 9. So what that tells us is, here, let me, I guess I'll write it, well, let's just write it like this. So I've done the work, and so what that tells us then is 5x plus 3 over 2x squared plus 5x plus 3 is equal to 9 divided by 2x plus 3 minus 2 over x plus 1. So if we were asked to integrate this right here, we would integrate this instead. So let's try another example. And this time let's do an actual integral. So let's compute the integral of 2 over x squared minus 1 dx. What we do to do this problem, what we do is we first say, let's just forget that we're actually doing calculus for a minute. Let's just do algebra. I need to figure out how to express x squared minus 1 in terms of partial fractions. So we say, all right, let's look at 2x squared minus 1. Factor the denominator. That's a 2 over x minus 1 times x plus 1. And we know then that that has to equal a over x minus 1 plus b over x plus 1. Right, so now our job is to figure out who the a and the b are that make this work. Get a common denominator now, so this will be a times x plus 1 plus b times x minus 1 all over x minus 1 x plus 1. Multiply stuff out, so we'll have an ax plus a plus bx minus b over x minus 1 x plus 1. Group the terms now, and so we get an a plus b times x plus a minus b all over x minus 1 x plus 1. Now we set up our equations. So we know that this fraction here has to equal this fraction right here, so the numerators have to match. How do we make the numerators match? Well, a plus b times x has to equal 0 because there's no x term here. So a plus b equals 0. Also, a minus b has to equal the constant term on this side. So a minus b equals 2. If we add these equations, we get 2a equals 2, which means that a equals 1. And that allows us to conclude that b equals minus 1. So now we return to the integral. Let me rewrite it up here. So the integral of 2 over x squared minus 1 dx is equal to the integral of 1 over x minus 1 minus 1 over x plus 1 dx. Right, so now we have an easy integral. This will be natural log absolute value of x minus 1 minus natural log absolute value of x plus 1 plus c. This answer is fine, but if you're checking your answers in the back of the book, they're always going to simplify using rules of logs. And so in final form in the back of the book, it would look like this. right? Remember, subtraction means divide, so this is natural log x minus 1 over x plus 1 plus c. Okay, so there's case 1. Notice we're just working on case 1. If we have distinct linear factors, we know how to proceed. Now, sometimes when you factor a polynomial, there's actually repeated factors. So case 2, we label, this is the repeated linear factors. And so that'll go like this: if q of x factors in the following way, a1x plus b1. Now, instead of just being raised to the first power like it was in the previous case, it's raised to some power, let's say m1. And then the next factor, a2x plus b2, raised to some power m2. And this can continue, a sub n x plus b sub n, raised to some power, call it m sub n. So let's say that we have a factorization of this form, right? Then the polynomial p of x divided by q of x can be written as a1x, a1 divided by little a1x plus b1 plus a2 divided by a1x, a2x plus b2 raised to the second power plus plus a sub m1 divided by a I made a mistake right here. Sorry. That should say, sorry, everybody, make sure you pay attention here. So I have constants in the numerator, and I want the bottom factor right here to be the same all the way through. So that should have been a little a1x b1 plus b1. And then this last factor will be an a1x plus b1 raised to the m1 plus other stuff, where the other stuff corresponds to the factorization of the other pieces. So what I've done here is I've shown how to get the partial fractions going for that term. And how does it work? Well, so let's say that this number right here is a 6, so m1 equals 6. Then we would have 6 partial fractions written down, a1, a2, blah, 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 or a3, all the way up to a sub 6. And the denominators are ascending powers of that first factor, a1x plus b1. And so that would be a 6th power right there. Then we would move on to the next one. So maybe this is a 10. Then I would have 10 partial fractions. Constant number 1, let's say b1, over a2x plus b2, plus capital B2 divided by a2x plus b2 raised to the second power. We'd have ascending powers until we get all the way to 10. So let's just, before we even start doing that, let's just see how this would go. So let's say set up the partial fractions. For, let's do 3x plus 1 divided by, and I'll write it in factored form, x squared x plus 1 cubed 3, let's not do a 3, let's do a 5x plus 2 raised to the second power. Okay, so let's not make it too complicated. Okay, so now what we do is we go factor by factor. Here's our first repeated factor. It's an x. You can think of that as 1x plus 0, right? So there's our first factor. Now, Because it's raised to the second power, there are going to be two partial fractions that we write down corresponding to that term. So it will be an a over x plus b over x squared, ascending powers. Then we move on to the next term. It's an x plus 1 raised to the third power, which means that we're going to write down three partial fractions with ascending powers. So it'll be a c over x plus 1 plus d over x plus 1 squared plus e over x plus 1 raised to the third power. Now we move on to the last piece. It's raised to the second power, which means that we're going to write down two partial fractions, and they will be f over 5x plus 2 plus g over 5x plus 2 squared. Now, obviously finding the a, b, c, d, e, f, and g, that's going to take a lot of work. I'm never going to have you have to work out that much. But what I want you to do is see the pattern right now. So theoretically, this is possible. A computer could easily figure out who those a through g's are, right? But understand the pattern. That's what I want you to do. Okay, so now let's try an example. So, as an example, let's compute the following integral. So we want to integrate 4x squared plus 3x plus 2 divided by x cubed plus x squared. So what do? We forget that we're integrating for a minute. We're going to do partial fractions first. And so we say, all right, the denominator, well, let's write it out. So 4x squared plus 3x plus 2 over x cubed plus x squared. Factor the denominator, and we get 4x squared plus 3x plus 2 over x squared times x plus 1. We've got a repeated linear factor here, a degree 1 term. And so now we write down the partial fractions. This will be at a over x plus b over x squared plus c over x plus 1. Now do exactly what we did before. We need to get a common denominator. So let's see, I need to multiply it by, so this will be a x times x plus 1. So I'm just going through the steps of getting a common denominator now. Plus b times x plus 1 plus cx squared, all divided by x squared times x plus 1. Now multiply everything out, so we'll have an ax squared plus ax plus bx plus b plus cx squared all over x squared times x plus 1. And now we group the terms. So this will be a plus c times x squared plus a plus b times x plus b all over x squared times x plus 1. All right, now we equate the terms. So compare this numerator right here with this numerator. That tells me that, sorry, that's supposed to be a squared right there. That tells me that a plus c has to equal 4. A plus b has to equal 3, and b has to equal 2. So that made life easy, right, having that b equal 2 there. So if b equals 2, that means that a has to equal 1. And if a has to equal 1, that means that c has to equal 3. All right, so now this integral, let's return to the fact that we're integrating, this integral will be equal to integral of a is a 1, so it'll be a 1 over x, plus b, which is 2 over x squared, plus c, which is 3 over x plus 1 dx. So now we've got an easy integral. This is going to be natural log absolute value of x plus, let's see, antiderivative of 2 over x squared is going to be actually negative 2 over x, and then we'll have plus 3 natural log absolute value x plus 1 plus c. This answer is fine, but your book would do something like this. Natural log absolute value of x over x plus 1 cubed, right? That 3 can be brought out as an exponent, minus 2 over x plus c. I would accept either of these answers on a test or a quiz, right? You don't have to simplify, but be aware if you're checking your answer in the back of the book, they're going to simplify as far as possible using rules of logs. So let's do one more example. And in this case, I'm not going to go through every step, but I want to compute the integral of negative x squared plus 3x plus 2. Oh, whoops, sorry, wrong one. Plus 3x, sorry, plus 10 divided by x plus 1 squared times x plus 3. So what you want to do here, forget that you're doing calculus for a minute, just do the arithmetic to find the partial fractions. So it'd be negative x squared plus 3x plus 10 divided by x plus 1 squared x plus 3. And the setup would go like this: a over x plus 1 plus b over x plus 1 quantity squared plus c over x plus 3. On a test or a quiz, I mean, occasionally you'll get one that has 4 equations, 4 unknowns. In those situations, I'd make it so that they work out nicely. 3 equations, 3 unknowns is more typical of what I would give you on an exam, maybe on a quiz a little bit more. Okay, so you would get common denominators, sort everything out, group the terms, equate the coefficients, and what you'll find, so I'll just say check, that a, so I work this one out, a equals 1, b equals 3, and c equals minus 2. All right, so if you do the partial fractions, you'll find this result, which means that this is equal to the integral of 1 over x plus 1 plus 3 over x plus 1 squared minus 2 over x plus 3. So now we have an easy integral. This will give us a natural log absolute value x plus 1 minus, so this is going to be 3 over x plus 1. And then we'll have a minus 2 natural log x plus 3, or absolute value x plus 3, plus c. This answer is fine, but in simplified form, we get natural log, it'll be at x plus 1 divided by x plus 3 squared, minus 3 over x plus 1 plus c. Either one of those answers is fine. So what this completes is, it completes our beginning of the study of partial fractions. There's actually more to go. So far what we've looked at is the situation where the denominator factors completely and all you see for x is powers of x is a 1, right? Linear factors. What we're going to look at next time is when, and this happens quite often, you factor a polynomial and you can't factor it quite this far. You'll have some quadratic factors and so on. Right? So we'll continue our study of partial fractions in the next lecture. All right? So see